It's great to welcome to the Journal Club a colleague of mine in that, John Taylor, who's a professor of oceanography here and has been on the faculty here since 2011. Before that, he did his PhD at UC San Diego, and then which won the Acritas Award for the best PhD in thermomechanics, according to the American Physical Society. And then he did a postdoc with Raf Ferrari, also part of the Schmidt community at MIT. And John's going to be talking to us today about OceanBioME, the modeling environment that he's added to the Oceananigans code. So very much looking forward to it, John. Thank you.
All right, thanks, Cole. Thanks for the invitation to talk. So yeah, I'm going to tell you about this model we've been developing. I'll tell you a bit about the motivation behind it, why we decided to do this, about how we've been building the model and thinking about it, and then I'll kind of walk you through one application of it. And just to say at the start, this is really work that is largely been done by Jago Strong-Wright, who's a PhD student here in Cambridge. And the other thing to say at the beginning is that we're building on amazing work from the Klima and Oceananigans team. So we're building this model that allows us to simulate the chemistry and biology in the ocean, along with some coupled feedbacks that I'll talk about. But we're building on this amazing package developed as part of the Schmidt team for Klima. And in fact, many of the developers of Oceananigans have been working on OceanBioME. This has been funded by the Center for Climate Repair, who's funding Jago, and a grant from the MAR Foundation. And one of the, I think from my perspective, an outcome of this could be collaborations with ICCS. I'd love to build connections with ICCS and work with the ICCS team. I think there could be a lot of benefit to that. And I'd love to hear your thoughts and questions, comments. Okay, so yeah, just as an outline, I'll start with some motivations. This is really less about the model, but kind of why we decided to build it. I should maybe say from the outset that, as Colin alluded to, I'm a physical oceanographer. My background is in physics and fluid dynamics, not necessarily in biogeochemistry, but we saw a need for a tool here and decided to work on this. And I'm really excited about it and the potential that it can do things it can do. So I'll give you the description of OceanBioME, and actually I'll show you the GitHub page. We can look at a few things there, and then I'll talk about an application that Jago's been working on, which is I think perhaps the most difficult application of OceanBioME you can think of, which is a giant kelp forest, where there's coupled physics, flow physics, interactions between the kelp and the flow, and also coupled biology as the kelp grows and interacts with the natural ecosystem, biogeochemistry in the water. Okay, so let's start with the motivation. And this really was motivated by the concept of marine carbon dioxide removal, or MCDR, is the acronym we usually use. So to first start quite broad, it's a somewhat old graph now, but from I think it was 2018 IPCC report. This is showing the net CO2 emissions, where the lines are positive. This is an emission to the atmosphere, where the lines are negative. That's CO2 coming out of the atmosphere in the net. Each of these are scenarios, possible scenarios, that meet the target of limiting warming to 1.5 degrees C. And the point I want to make by showing this graph is that nearly all of these scenarios require some net negative emissions. They require carbon dioxide to be removed from the atmosphere actively. So this is what we call carbon dioxide removal, the idea of removing carbon dioxide from the atmosphere. In fact, now some of these pathways, if you start rather steep. So if you have drastic emissions cuts, then you require less. Later on, unfortunately, we're drifting towards this curve here. Probably, maybe in the best case scenario, that we're going to require, the longer we wait, the more we emit, the more we'll have to remove later, essentially, to meet these targets. There's an important point to make with a very simple graph here. So there are huge numbers involved. We've been emitting somewhere in the range of 40 tons of carbon dioxide per year. So they're kind of symbolized by this big graph. What I'm going to be talking about are ideas and technologies that could get us to 1 gigaton. This is tiny compared to the total, so it's a really important point to make that this is not a substitute for reducing emissions. If we don't produce this, there's no point to doing that. And it's much, much easier to stop emitting than it is to pull CO2 out of the atmosphere. It's a very dilute gas. Thermodynamically, it's much easier to stop emitting. So that's a very important point to make. Nonetheless, we will need to remove CO2 from the atmosphere at some point. And personally, I think it's very important to try to understand how we can do that. What are the best strategies, the best ways to do that? What are effective tools? And how do we minimize impacts as we're doing it? Just to put the numbers in perspective, this is a little bit unfair, but this is you might have heard this direct air capture plant, so DAC. Basically, it's in engineering where this group, Climeworks, is pulling CO2 out of the atmosphere directly, out of the air. It's big fans blowing through here. And then the idea is to store that CO2, say in saline aquifers, in a relatively permanent way. Admittedly, this is a test plant, but nonetheless, if you kind of think about the scale of this, this is the largest one active now. Just to get to 1 gigaton, you need 250,000 of those. So we're talking about huge numbers. It's a massive, massive challenge. Now, one of the reasons that the ocean is promising is because of its massive area and energy. There's a lot of light, a lot of sunlight hitting the ocean. So we have a lot of surface area and a lot of energy. And in fact, the ocean has been a significant net sink of carbon and CO2 over the years. This is 60 years of data-ish. There are two axes here. This is gigatons of carbon per year, or we can think of gigatons of CO2 per year, which is what we're doing. Right now, the ocean is in the net taking up about 12 gigatons of CO2 per year. And it turns out the ocean has taken up about a third of what we've emitted to the atmosphere. So about a third of what we put in is not gone to the atmosphere, it's gone to the ocean. Now that leads to its own problems. That's caused ocean acidification. As there's more CO2 dissolved in the seawater, the ocean becomes more acidic. That has negative impacts on a lot of marine life. But this also shows the ocean's ability to reach big numbers, essentially. Okay, so what is marine CDR in that context? So first, CDR, or maybe you could terrestrial or engineering, this could be planting trees or things like direct air capture. Essentially remove CO2 directly from the atmosphere. And either store it in biomass, soils, or subsurface geologically. Marine CDR, or sometimes ocean CDR, is a little bit different. This is more indirect. So essentially all of these methods the idea is to remove carbon from the surface water. Now you can either do this directly, so there are methods kind of like the direct air capture, called direct seawater capture. You can remove the carbon directly from the seawater and maybe store it somewhere. Or you can take carbon from the surface and move it to the deep ocean. And the deep ocean is a massive reservoir of carbon in the Earth system. There's far, far more carbon in the deep ocean than there is in the atmosphere, for example. There's also very slow timescales, so if we can sequester some of the CO2 in the deep ocean, it will stay there for many years. This is indirect because we're not directly changing the atmosphere. But if we remove CO2 or carbon from the surface ocean, reduce effectively partial pressure of CO2 in the seawater, the ocean then has the capacity to take up more CO2 from the atmosphere. This also has the effects, by the way, of alleviating to some degree, at least locally, acidification of the ocean because we're reducing CO2 levels, again, at least locally. Imagine ways of getting a co-benefit from doing this. And there have been many ways proposed, many techniques proposed to do this. As I mentioned, some of these are direct. So this is like direct seawater capture with some electrochemical technique, taking in seawater and then storing CO2, say geologically. But others essentially use or try to build on natural processes, either stimulating phytoplankton, marine macroalgae, or macroalgae, kelp, seaweed, or altering the ocean chemistry and allowing the ocean to take up more CO2 that way. I'm not going to get into much detail here. I will come back and talk about kelp later on. This would be a whole different talk. Now, I'm thinking kind of broadly about MCDR. I think this is, right now, this is limited by two key factors. So the first is our still somewhat limited understanding of the coupled physical, chemical, and biological processes that happen in the ocean. We know they're very complicated systems, and all of those, and they interact on a variety of time scales and space scales. But I would argue that an improved understanding of these systems is going to be needed to predict both the effectiveness and the impacts of MCDR before we do it, so we can plan appropriately. The second barrier now is the acronym, so jargon's MRV, monitoring, sometimes measuring, reporting, and verification. So it turns out this is, in the ocean, this is much more difficult than it is in other realms. So we either kind of direct air capture or say reforestation, where you can come back to the same place and do surveys and measure soil chemistry and so on, estimate how much carbon is in the system. The ocean is a very dynamic place. The water doesn't stay in the same place. And so what you do in one place is going to have an impact and effect elsewhere. So one of the key problems here is tracking the water in this dynamic ocean. And just to illustrate this, there's first a time scale. So it turns out that it takes, this is a map of the CO2 equilibration time scale. And you can kind of think of this, well, if you made some change, perturb the system in some way for equilibrium, this is how long it would take to come back to equilibrium. And in much of the ocean, it's pretty long. It's maybe it's about 1 to 12 months. It varies. It's on the sort of month time range. And then you can ask, well, for a local source, what happens to the water? This is a movie, just kind of a demonstration from Matt Long at Seaworthy, showing, so there's an ocean model underneath here with ocean eddies and some currents. There's some winds blowing over, some storm at the end. And they're releasing a tracer here. And you can just think of that as tracking the water. This is going to run over 12 months, sorry, 5 months, I think. And over the period of 5 months, this plume of tracer, basically the water that was felt that source, that would be affected by that source, spreads out across hundreds of miles. And if you compare this, if you think about tracking the carbon, and we need to understand where the carbon is going into the ocean, it's going to take months for that to happen, for that to equilibrate. You know, you think about a system that spans this enormous area and makes that sampling and monitoring very difficult. And I think it's very clear from this sort of picture that models have to play a role. I think probably impossible to imagine doing this entirely with direct measurements. It's just the space and time scales are too vast to really cover, at least cost effectively. Now, on the context of models, there are 3 types of models. So we can kind of break it up this way. So of course, we think of Earth system models or global climate models where you run on the whole globe, via level on grid, span the whole globe. Often when we're studying a particular region, this is the coastline of California. I'll come back to this at the end. We might want to run a regional model, which is often nested within a larger scale model, maybe ultimately a global model. And often for numerical purposes, we have nests where we kind of hierarchies where we sort of step down, increasing the resolution each time, but decreasing the scale. One of the other challenges of MCDR is that typically, this varies a little bit depending on which intervention it is, but typically the intervention sites are very localized. So you might be doing something, maybe this is a seaweed farm. If you think about the typical size, it's actually pretty big, but if you imagine this being a seaweed farm, the resolution of even a regional model is not high enough to capture that. You're only going to resolve things that are several grid points big. So this would just be a little pinprick, even in the regional model. This, though, is where we're getting the most data. So if you imagine this is a seaweed farm, you might imagine some sensors maybe around or inside the farm where you're collecting data. But again, these would look like pinpricks on the scale of one of these models. So when we're doing local interventions, we need to think about a new model. We're calling this a near-field model to capture these really highly local effects. Now, an application is that the physics on this scale, what's happening on this scale, are fundamentally different than what happens on the water scales. So in building models of this type, for example, we often assume that the pressure is hydrostatic. And this simply doesn't work if you want to resolve things that are down at sort of meters or tens of meters scales. So we need a different type of model. And this is where Oceananigans comes in. One of I'll talk more about Oceananigans in a minute, but one of the key aspects of Oceananigans is it can span this whole range of scales. You can use the same model, same physical model. Well, we should say the same modeling package maybe, but they have different dynamics, different solvers to capture the global scale. And the ocean team is doing this at the global scale, and you can go all the way down to very, very small scales and capture some of this three-dimensional motion that might arise. And I'll show this later. Okay, so as I said, we're building OceanBiome on top of Oceananigans, on top of that framework. Both models are written in Julia, the Julia programming language. Both models are fully open source and are collaborative. We're meant to be collaborative from the beginning, and really are. I really see these as the OceanBiome is a community tool, and I hope it continues that way. We've already had a lot of input from the community on this. So I mentioned Oceananigans. It's a really incredible model. The team has done a fantastic job. They have a series of flexible solvers that capture both hydrostatic and non-hydrostatic physics. And you can go all the way down to direct numerical simulations. In fact, the PhD students, Andrew is working with Colin and myself, is using Oceananigans for called direct numerical simulations. So this allows very multi-scale simulations. It's also optimized to run fast on GPUs. So both codes are really written with that in mind. And as I'll show, this leads to a step change in what's possible in OceanBiome. This is also kind of a partial list of names of developers. These are the co-authors on a paper in Journal of Open Source Software, which outlined some of the things about OceanBiome. It was published at the end of 2023. But I just had more people contribute to this since then. So this is the idea for OceanBiome. So as I said, the physics are handled by Oceananigans. So that would give us velocity, temperature, salinity variables. OceanBiome is, you can kind of think of it as a set of packages that each of which are modular. And the idea is that we can pull modules from each of these. We don't have to use all of them, but we can pull modules from them as we want. And we can pick and choose and combine them in a modular way. So OceanBiome has models for the seawater biogeochemistry. This includes, for example, the dissolved nutrients, nitrate, phosphate, and so on. Phytoplankton, this is handled as a concentration field, and zooplankton, perhaps sinking particles, detritus, and so on. We have 3 or 4 biogeochemical models implemented, spanning the range from a very simple 3 or 4 component model to an intermediate complexity 7 component model to a full complexity IPCC class to a 24 components model that we added this summer. And you can pick and choose these. We also have models for the carbon chemistry. So basically seawater chemistry, where we essentially tracked 4 things: the dissolved inorganic carbon, alkalinity, the seawater pH, and the partial pressure of CO2. Just to say that we assume that these are in equilibrium. And if you're in a state of equilibrium, you can specify 2 of these, any 2 of these, and you can solve for the other 2. So we have solvers for those, and I'll show an example of that in just a minute. This is important because this links with the air-sea gas exchange. We have some, we have code, several modules with different ways of handling this to calculate the air-sea gas exchange of oxygen and CO2 in this case. We also have a model at the bottom that's sort of on the top. At the bottom, we have models for the sediment. So what happens when the carbon gets down into the seafloor and sediment and decomposes and releases carbon back to the seawater. And finally, we have this box. So this box is something that I think is unique, or at least relatively unique. You don't see this very often. So this is what we're calling, we just didn't know what we're calling biologically active particles. So we're building on top of a feature in Oceananigans, which are particles. Typically, these are biogeochemical, meaning they move with the seawater. But here we have active particles that can have their own physics and can have their own biology and chemistry. So they can interact with the flow, and we'll see this as an example with kelp. So the kelp can be treated as an active particle, or a series of active particles. But they can also interact with the seawater biogeochemistry. So the particles can take up nutrients, for example, as they have something growing, like in the case of kelp. It'll take nutrients out of the seawater, maybe release carbon back into the seawater. So we have a coupling between the particles and the tracer-based biogeochemistry. And of course, these can also interact with the carbon chemistry. And let me just say that this sort of handling of this is done in OceanBiome through these kernels. So you have the particles are at some localized position in space. We have these kernel functions that allow you to interact with the neighboring grid points with a certain stencil you can specify. So I thought I would just quickly show you the GitHub page for OceanBiome, and I'll show you a little demo. So this is our GitHub page, and I encourage anyone to check this out with a little README here. We have Jaco's done a terrific job, and other contributors done a terrific job with the documentation. So this is our user guide. One of the amazing things about using Julia is the package manager. I mean, it's kind of like Python. As someone I won't name the ocean model, but for the last month or so, I've been trying to run some benchmarks comparing the performance of OceanBiome to a traditional ocean model written in both C and Fortran. The install guide, so the user guide to install that model was many pages, and it required the user to both download and compile 7 or 8 external packages, right? So it's a huge process. To install OceanBiome, you download Julia, then you do this and that, and it's installed. It'll go and install. It installs the compatible version of Oceananigans and all of the other dependencies. That should just work. So I have a new appreciation for this. Okay, so this also explains how. Or kind of the front page here explains how to run the example that was shown on the README. There's a movie shown on the README page. It shows the code for this. It's kind of a pretty short script here. Here, so we have some other examples you can look at here. These are the model components. So the things I described. So the biogeochemistry, air-sea gas exchange, carbon chemistry. I might just show the carbon chemistry. So this is the page for the carbon chemistry. So we can define this function which returns, in this case, the partial pressure of CO2 or the pH. So I said we can define, say, the DIC in alkalinity and return the partial pressure, or in this case, actually fugacity of CO2. And down here we have a description. We'll go through this. We have a description of the chemistry that's going on behind the scenes here. And hopefully, we'll make it easier for users to see kind of what the code is doing. The other thing I might just mention here is we have a page describing how to implement a new model. So we've tried to write this in a way that makes it really easy for people to come in and write a new module in one of those sections. So write a new biogeochemical model, for example. And this walks the user through how to do that. So if you wanted to build a new biogeochemical model, you would go through these steps, and it gives a little example of how to do that. And by the end of this little tutorial, if you like, it has a model for the sediment. It's tracking the, in this case, nitrogen in the sediment as a function of time. And it simulates a little phytoplankton bloom where nutrients are consumed, phytoplankton increase, the material falls down and makes its way onto the seafloor. So I wanted to talk about two, and then I'll sort of wrap up here, I think, about the code, but talk about two amazing features of Julia. It really, as someone who I spent about the first part of my career programming in Fortran, this has been a revelation for me. So we using in the Julia ecosystem, we can take advantage of composability, and we're trying to write OceanBiome in a way that takes advantage of that. And what I mean by that is we can use OceanBiome, I mean, both with itself and Oceananigans, but also with other packages. And this is a little example of that. So this is just OceanBiome on its own as a standalone, using one of these functions from the carbon chemistry that I pointed out. And here we're using a package called measurements. So the notation is really intuitive. So what this does is so imagine that you have measurements of the DIC and alkalinity, so those two components of the carbon chemistry. Julia allows Unicode, so if you do a little plus minus measurements, and you're using this measurement package, measurements will interpret this now as a new type. It's a measurement type. And it knows that when you do this, this is the value and this is the uncertainty. Okay, now this thing is now a measurement type instead of a floating point. But we can operate with OceanBiome with a measurement type just like we would a floating point. So we could send in floating point values here, and it'll give us the fugacity. That was actually an example on the preview page. Or we can send in these measurement types. And if we do that, we get a measurement out. And the measurement out then is the value and uncertainty of, in this case, the fugacity. Okay, so it just knows that, and it's doing this measurements package is doing the error propagation through the code as we go through. So all the operations of the code will handle the errors. So a really intuitive way, and then we got this plot. So this is now. Oh, but by the way, we're plotting here. So this is a scatter, but just at one point. The plotting package knows to plot both the value and the errors. So you could do this without error bars, 650 scalars, just a point. So this would be incredibly useful for, for example, designing an instrument. If you have an instrument, you know that there's going to be some uncertainty, some measurement error. You can infer what the error will be, and the thing you actually want to know, which is in this case is the FCO2. Okay, Julia also uses a paradigm called multiple dispatch, where you can call the same function, and depending on the types, depending on what you're sending in, it will behave differently. So, for example, Jaco's written this function in a way that if you send it DIC and alkalinity, it will calculate the pH and FCO2, the other two unknowns. But if you send in DIC and pH, it will calculate alkalinity and FCO2. So you can send in, you can say, well, actually, maybe another sensor, instead of measuring DIC and alkalinity, maybe a different sensor is going to measure DIC and pH, and I have its own error bars. So you can send in the DIC and pH instead and get the FCO2. And then you can say, okay, depending on the accuracy of this sensor, you'll get some accuracy, some error bars here. Maybe this is a little bit smaller, a little bit more accurate, perhaps, given these levels. You can imagine how useful this is for kind of prototyping and thinking about measurements. And from a user's perspective, I kind of feel it's almost magic. You just kind of give it the things that you have, and it just works, which is pretty amazing. And finally, I would say a few words about Oceananigans. So that it's a really amazing effort, incredible code that this team has developed, the Kalima team. And we're really taking advantage of that. So everything we're doing is building off of what they have and taking advantage of the capabilities they've been developing. I mentioned the GPU performance. This is one of the things that I think is really transformative for ocean modeling. This is a figure from a recent paper from Simone Silvestri showing, maybe you've seen this, okay, these are various ocean atmospheric climate models in these circles here. They're measuring performance in terms of power. So this is the simulated years per megawatt hour that units they're using. It's a bit tricky to compare. If you're comparing GPUs versus, these are basically all CPU, running on CPUs, and the Oceananigans is running on GPUs. So it's, think carefully about how to interpret these things or how to do that comparison. But this is one way of doing it. And on the x-axis is the number of grid points. IPCC models over here on the left. These are quite high resolution models. This effectively is the current state of the art. And they've shown that in this paper that Oceananigans can really push past that significantly. This is, these are log scales. So either in terms of performance, kind of going from the state of the art, or in terms of the resolution and afford at a given power output level. It's a step change. It's a factor of 10 or something for each direction. And as we'll see, this lets us do things that you just couldn't do otherwise. A couple examples now of using Oceananigans and OceanBioME together. This is a simulation of the upper ocean, turbulence in the upper ocean. So we have a little patch of water that's 1 kilometer square. In this case, we're just simulating the top 140 meters of water. There's what we call a sub-mesoscale eddy that's generated here, which you can see in this swirl. Jacob's made this really nice figure visualizing fields from ocean biomes, so nutrients, phytoplankton, dissolved organic matter, and dissolved inorganic carbon. There are other fields too, but these are 4 of them. And then the other thing we have in this is to demonstrate the particles. So inspired by some work by a company called Running Tide, they were thinking about seeding buoys, which are here, that float along the ocean surface and grow kelp, or seed them, kind of a rope, and kelp is growing up the rope. So what we've done is we have these buoys that are floating around. They're at the surface, but they're getting moved. This is really just using ocean, it's getting moved with the surface currents. But now using OceanBioME, we can solve a growth model. So this is from a model for shear kelp, which is what running time we're using for a while. And we can solve for example, the area of the kelp farms as a function of time on these paths. The reason they differ is because they're exposed to different nutrients. But then as they're growing, they're also taking, you can't really see this, but they're taking up nutrients. So these are coupled. So that as kelp is growing in that buoy, it's taking out nutrients from the surrounding water. And it's also interacting with the carbon chemistry. This is fully coupled system. And I'm used to models, actually just on the physics side, I've been running models like this for a long time. And I'm used to a model like this taking a few days to run. This with 2 meter resolution took an hour to simulate 5 days. And you can just imagine for prototyping, or of course, we're expanding to bigger scale, this is really a step change. Just a quick example of running OceanBioME globally. So one of the really nice things, and one of the reasons that we wanted to use Oceananigans, is we could start with something small scale like this. You can imagine kind of testing your model using data that's generated locally. You can use the same biogeochemical model, OceanBioME, and run it instead with the global model. and now expand out to see what would the impact be or effectiveness if you expanded this out to a much bigger area. So that ability to scale from global all the way down to very local scales was really important for us, and something that Oceananigans afforded us. And again, this runs, this is a coarse resolution model that just took 45 minutes of wall time to simulate a year. Okay, so in the last, I'm only going to have questions, but maybe the last 10 minutes or so. I want to show an example of using this. This is a paper that some results that Jacob just published, where we're simulating a kelp forest. I think perhaps the hardest example of using OceanBiome. This is a picture of a kelp forest. So this is giant kelp. When I, as Colm said, I did my PhD in San Diego, I never learned how to surf, but I did learn to scuba dive. And there's a kelp forest just offshore in La Jolla. And it was my favorite spot by far to go scuba diving. It's just an incredible environment to be in. Really otherworldly. Interestingly, beautiful kelp are important. It's been estimated they naturally sequester something like 170, there's big air bars in this, but something like 170 megatons of carbon per year. And this basically happens through two ways. Either pieces of the kelp break off and get buried in the sediment, perhaps locally or somewhere else. Or the kelp drift. In the case of giant kelp, they have these gas vesicles called nematocysts. So they float, they're buoyant, and they'll float for a while, eventually sink, and maybe make their way to the deep ocean. And that is also a kind of a long-term sequestration mechanism. So of course, if these things are growing and it washes up on shore and the kelp decompose there, and then moves into that sink of carbon. And there have been some methods proposed to expand this to offshore waters. You could do this either in a farm, say in coastal waters, or you can imagine growing kelp. So I mentioned growing kelp offshore somehow, either with free drifting buoys or moored farms. One of the challenges you have is that, this kind of aside, one of the challenges you have is that far offshore, there tend to be, depending where you are, there tend to be low nutrients in the surface water. So you might think about ways to either get the kelp down to where there are nutrients or to bring nutrient-rich water up. That's sort of a different topic. It has been estimated that growing kelp, expanding kelp farms, having kelp farms globally, could sequester a significant amount of carbon. This is just an example from this paper in Nature Plants in 2022, where a gigaton, to sequester a gigaton of carbon required about 0.1% of the ocean area, which is that area, which is big, a big kelp farm, or a lot of small kelp farms. But actually, if you put that in context, the UK's EEZ is 6 million square kilometers. So large than the world. So actually, it's a big number, but this is global. Maybe this is global. Now, they also talk about economics. So there's a little side here that kelp is, can be very valuable economically. So you can harvest the kelp, use it, for example, for biofuels, which won't sequester carbon, but will offset other emissions. And they suggested that actually this, at least in the immediate term, more cost effective. Other approaches of things you can do with the kelp. Okay, what we've been doing, this is Jago's work, we've been essentially using a natural kelp forest as an analog for MCDR. And the idea is that, well, there aren't really large-scale kelp farms now. There's some pilot farms, but not really large scale. So, but we can instead go to a natural kelp forest, and we picked one that is very highly instrumented. There's a long-term observing record. It's been kept by scientists at UCSB. This is an example. This is one from the one we're using. It's Mohawk Reef, which is here. So Santa Barbara is here, which happens to be where I was born. This is a picture of the kelp forest from this paper here. Now, one of the key questions when we're thinking about kelp and both their growth and their contribution to carbon is transport. So understanding the transport through the kelp forest is really critical. This is important for two reasons. One is that, so kelp have this famous capacity to grow fast. They can grow something like 1.5 feet a day under ideal conditions. But they're also very nutrient hungry. They use a lot of nutrients from water as they're growing that fast. And so their growth can be nutrient limited because they'll pull nutrients out of the water surrounding them. And so if you don't have enough nutrients, basically that growth rate can be constrained, can be limited by the flux of nutrients into the kelp forest. So how fast the water moves through the kelp forest is important for their growth, but it's also important for the redistribution of carbon. If you have kelp pieces or dissolved carbon in seawater, and that's exiting, you want to know how fast is it leaving the forest and where does it go? These are two previous studies. This is the same kelp forest. This is Mohawk Reef. In summer and in spring, it changes seasonally, so it has growing seasons. And this is the tidal flow. So this is the flow through both, actually the means are the arrows, and then the tidal flow is indicated by these ellipses. I might just keep this in mind. There's a net flow into the kelp forest and offshore. If you look at these little arrows, and I'll come back to that in a minute when we talk about the model. There was another paper, there's many papers on this, but another one to highlight. This is a really nice paper from Joanna Rossman and colleagues at Stanford, where they had a flume, they had water going through this flume, and they had a little laboratory model of the kelp. This is rubber tubing connected, and they're attached with fishing floats to keep them buoyant. And then they have fronds and sort of flags at the top to mimic the drag. Okay, so we've been using OceanBioME to do this, and this is a demonstration of the capabilities of the active particles that I mentioned. So the active particles can have their own physics in addition to their own biology. And what we've done is we built on a model that was first proposed by Utter and Denny and then extended a bit in that paper from Rossman et al. So essentially our model for kelp are elastic bands. You can kind of think of like the surgical tubing from the experiment. Connected with nodes, and the nodes are buoyant relative to the water, so lighter than water. Then we can have several of these strung together, and then we calculate the forces, the tension. We also have elasticity; these can stretch. We calculate the forces, and then the acceleration, the movement of each of the nodes connected by these links. And this is a little demo. So here, this is a single strand of giant kelp in our model. Connected with these little floating points and strands. And this is just now an oscillating flow back and forth. This is kind of like waves. This is a pretty fast flow going back and forth. You can see the kelp deforming. They're pulled by the flow. They move back and forth and sort of sway, you might expect. The other thing that is happening here, you can't see it in this model, but I'll show it in a minute, is that there's another coupling. So there's influence of the physics on the kelp, but the kelp also exert drag back on the flow. So the kelp will slow down the flow. The forces are equal and opposite. So we have a couple of physics going on between the kelp and the flow. Okay, so I'll show some simulations that Jago are in, and these are things I just don't think would be possible without a GPU. So it's a pretty big box for a simulation like this. This is a large eddy simulation with resolution of several meters, 5 kilometers. This basically captures the tidal excursion. The tides go back and forth here. We're forcing the tides. We have a localized kelp forest. The size is more or less set from Mohawk Reef. The water depth also matches Mohawk Reef, just 8 meters in this case. We've tested that model. Oh, and by the way, so within this kelp forest, I can't remember the number, but within this kelp forest, we have kelps, a bunch of these models. So we have models like this, many of them seated in this patch. I think it's hundreds of kelp inside here that are all moving back and forth. You'll see them. Okay, so we validated the model using both the lab experiment data. This is now a mean flow coming on. You see actually the canopy is more dense, so this is the current speed. It slows down more at the surface. There's drag at the bottom. So actually the maximum velocity is somewhere down below where there's less drag and less biomass. And we've also compared with some data. So we've made synthetic data, which are these points here, sampled at 2 stations that are more or less placed where data was collected from that Gaylord paper from the field. And the Gaylord line, their sort of best fit line is that gray line with the 95% confidence interval in the shading. The black line is the fits to our model data, and it matches quite well. Essentially, we're capturing the drag from the kelp forest. Okay, now the other thing we did was, because we're interested in the flow through the kelp forest and the exchange of either nutrients or carbon or something else dissolved, we solved for a tracer. So it's a tracer that satisfies essentially the advection fusion equation. We're parameterizing the fusion here through some grid scale flux. Get into details of that. But then importantly, we add a source. So we have this source term here, and the source term is formulated so that this tracer is saturating. So we have the saturation value, which we're arbitrarily setting to 1. So if C is equal to 1, then this forcing goes away. But if C is smaller than C naught, little c is smaller than C naught, then this will increase towards C naught and vice versa. The time scale here is mimics, this is from another paper, mimics the uptake of nutrients from kelp. The typical time scale for the uptake of nutrients. And then what we did is we varied the kelp forest density. So we varied the density, basically how many fronds or how many individual kelp are represented within each grid cell. And we varied this density from 0.25 to 3 individuals per meter squared. The typical values are around 1.5 to 1 or 2. So it's kind of spanning a range that captures natural kelp forests. And we're interested in that parameter. And just to show you now a movie of what happens, this is the tracer being released by a kelp forest. The tracer was 0 everywhere. If you can see the little lines, this is the surface canopy. This is the kelp at the surface. They sort of stretch out, so you can see the lines are elongated. I'll play that again. As the tide goes back and forth, this is now 10 hours, kind of small. You see the tracer being released, you see the kelp deforming, it forms a wake, this turbulent wake behind the kelp forest. So I said there's coupled physics and biology going on here in a really complicated and I think interesting way. Skip through some of this. I think one thing I just wanted to point out, which you saw in that video, I think, which is linking back to the observations, is the kelp forest deforms. It forms this kind of lozenge shape. It starts off as a circle, but the canopy actually ends up being deformed. Well, what we did to try to understand this, we looked at the mean, the time average flow, the time average circulation. And it turns out the time average circulation is going in the direction the tides are going back and forth like this. So the time average flow is into the kelp forest in the direction of the tides, and then out of the kelp forest in the direction perpendicular to the tides. And I think a simple way of explaining that, or understanding it, is in terms of the tides. So if you're sitting here, and imagine the tides are moving from left to right, then you're feeling the full tidal velocity. You're going to be at the maximum tidal velocity. Okay, in this phase of the tide. When the tide's reversed and it's going this way, now you're in the wake of the kelp farm, or sorry, kelp forest, and you're experiencing low velocities. And essentially that bias that you're seeing the high velocities on the upstream side, the low velocities on the downstream side, leads to the mean flow this way through the kelp forest, and it has to go somewhere, so it goes out the side. This is the depth integrated, I should say, so it can't go down. This is the depth integrated depth average flow. And you can sort of zoom in and see that the kelp are deforming in the same sense. And you can kind of understand that, go through the same argument, say the kelp will get pushed over more when they're feeling the flow coming this way, but then when they're in the wake of all on the side, when they're in the wake of everything here, they won't get pushed back as far. They form this shape. And as I said, this pattern, so the Gaylord, there was a coastline here, so you could go towards the coast, but we did see that mean flow going through the kelp forest in a very similar way. So I think I'll wrap up here. I'm going to hopefully convince you that this is a new useful tool for ocean modeling, and for particular connecting ocean physics and biogeochemistry. I mentioned my background is in the physics, but I think one of the things that I would really love to enable is closer links between these disciplines of physics, biology, and chemistry. And I think software like this can play a really important role in doing that and facilitating that, making it easier for people to understand how these things talk to each other. And I hopefully demonstrated that we can simulate pretty complex things with this package. A couple of things that we're doing in the future, and we could go on and on about this. We're thinking about some other case studies, so including an offshore kelp farm. There's another PhD student, Jenna Andrews, who's studying this. I'm also interested, we're not working with this actively, but I'm interested in the upland enhancements. We have the carbon chemistry, so we could do interesting things with that with OceanBioME, or other people could love to hear contributions there. One thing that I'm really interested in is connecting the model with data. And this is something that's quite different when you're dealing with a biological or chemical system. Unlike the physics, there's perhaps more uncertainty in the equations that we're actually solving. And I think bringing in data plays a really big role here. And it's something that we're thinking about how to incorporate data simulation and uncertainty quantification into OceanBioME. I'd love to have thoughts and input on that. Another thing I thought it would be really nice to have a user interface to make this easier, especially if someone doesn't have a background in ocean modeling. So to really enable scientists and practitioners to use tools like that. So I'd love to hear from you. You can email me or check us out on GitHub, open an issue or leave a comment there. Brilliant, thanks.